When you throw a ball, it traces a beautiful curve through the air. But here is the secret to unlocking this flight. The ball is actually living in two separate worlds at the exact same time. It moves forward, and it moves up and down, completely independently. Let's sketch this path. As the ball travels along this curve, we can split its motion into two distinct arrows. The horizontal velocity, which we'll draw in blue, points straight ahead. The vertical velocity, drawn in orange, points straight up and down. Notice how the forward arrow never changes its length, while the vertical arrow shrinks, completely disappears at the peak, and then points downward. Why does this happen? Because gravity only pulls straight down. It has absolutely no effect on how fast the ball moves sideways. This means a projectile is just a constant speed horizontal cruise combined with a vertical freefall, happening at the exact same time. Now, let's look under the hood at the mathematical engine driving this flight. Horizontally, there is absolutely no force pushing or pulling the projectile once launched. This means the horizontal velocity, v_x, remains completely constant. The equation for its position is beautifully simple. Horizontal distance equals the initial horizontal speed times time. Vertically, it is a completely different story. Gravity is constantly pulling downward, causing a steady acceleration of g, which is about 9.8 meters per second squared. This constant pull means the vertical speed changes every second, and the distance fallen grows quadratically with time. When we run these two independent mathematical engines at the very same time, we get the classic parabolic path of a projectile. Notice how the horizontal velocity arrows stay exactly the same length, while the vertical velocity arrows grow longer and longer as gravity takes over. They work in perfect harmony, completely ignoring each other. Now, let's trace the physical path itself, the trajectory. When a projectile is launched, its path is always a perfect mathematical parabola. It all starts here, with the launch angle, which dictates how much of our initial speed goes into fighting gravity versus covering ground. As it climbs, gravity relentlessly slows down its upward motion until it reaches this peak height, which we call h. At this exact peak, the vertical velocity momentarily drops to zero, while the horizontal speed keeps coasting along. Finally, the projectile descends, touching back down to Earth. The total horizontal distance covered from start to finish is the range, denoted by r. Together, these three key variables map out the entire anatomy of flight. Let's put our equations to work with a concrete example. Imagine kicking a soccer ball at 20 meters per second at an angle of 30 degrees. First, we break this initial velocity into its horizontal and vertical components. To find the peak height, we look purely at the vertical motion. Gravity slows the ball's upward climb until its vertical velocity hits zero at the peak. This takes just over 1 second, reaching a maximum height of 5.1 meters. Finally, how far does it travel? Since the path is perfectly symmetrical, the total flight time is double the climb time, or 2.04 seconds. Multiplying this by our constant horizontal speed gives a landing distance of 35.3 meters.